Hey students, Professor Nugent here. We are going to introduce Chapter 5 in this video. In Chapter 5 we discuss hypothesis tests and confidence intervals for regression with a single regressor. We'll focus on hypothesis tests for the slope of the regression line and confidence intervals around that slope. Here's the outline of what we will discuss in Chapter 5. We'll look at the standard error of the OLS estimator of the slope. We will discuss how to carry out hypothesis tests concerning the value of the population slope. We'll construct confidence intervals for beta 1. We will look at regression when the independent or when the independent variable is binary, so when it takes just two values, yes or no, 0 or 1. We discuss heteroskedasticity and homoskedasticity, which describes different conditions for the variance, and we will discuss the efficiency of OLS and the student t-distribution. A big picture review of where we are going. We want to learn about the slope of the population regression line. We have data from a sample, so there is sampling uncertainty, right? When you are random sampling from a population in different, you have the possibility, the chance of drawing different samples each time that you sample randomly, and so there's sampling uncertainty about the OLS estimators. We want to then learn about the amount of uncertainty around the value of the slope of the population regression line. There are 5 steps toward this goal, and we have completed much of them. Okay? So, number 1, we're going to state the population object of interest. In most cases, at least in this chapter, the population of interest is going to be beta 1. We will provide an estimator of this population object, which will be the OLS estimator beta 1 hat. We're going to derive the sampling distribution of the estimator, and this requires certain assumptions, like our least squares assumptions for causal inference. In large samples, this sampling distribution will be normal by the central limit theorem. We have shown this in Chapter 4. The square root of the estimated variance of the sampling distribution is the standard error of the estimator. So we have calculated an expression, we've come up with an expression for the estimated variance of the sampling distribution. Now the square root of that is our standard error of the estimator. Then we'll use the standard error of the estimator to construct t-statistics, test statistics, for hypothesis tests and for confidence intervals. So we have gone through steps 1 through 4, and now we're going to pick up at step 5. Again, the object of interest is beta 1. Right, we have a population regression line. That population regression line is given by equation 1. yi equals beta naught plus beta 1 times xi plus ui for observations I equals 1 through n. We are interested in the population slope, beta 1, the slope of the population regression line. The estimator of beta 1 is the OLS estimator beta 1 hat. Now we're getting at the sampling uncertainty around the OLS estimator beta 1 hat. Okay? How good is the OLS estimator beta 1 hat at estimating beta 1 for that sample and population? So because the population regression line is given by the expectation of y given x is beta naught plus beta 1 times x and the expected value of ui given xi is 0, okay, we can derive the large sample distribution of beta 1 hat assuming that the observation xi, yi, or observations I equals 1 through n are independently and identically distributed, and that large outliers in x and or y are rare. So we have the second and third least squares assumptions, right? This is least squares assumption 2. This is least squares assumption 3. Up here, we are assuming number 1, right? Expected value of ui given xi is 0. That we cannot predict the value of the OLS residual given the value of x. From this information, we have shown that for large samples, for n large, beta 1 hat is approximately distributed normally with a mean or expected value of beta 1, and so beta 1 hat is unbiased because the expected value of beta 1 hat is beta 1, normally distributed, and a variance of sigma squared v over n times the square of the variance of x. So the variance of v over n times the square of the variance of x, where we have defined the variable v as equal to the product of ui times the difference of xi and the mean of x. Okay. Now we want to take the square root of this variance to get the standard error, and we're going to use that together with this result that the OLS estimator of beta 1 is normally distributed. We have the standard error and the result that it's normally distributed. These two things are going to help us carry out the hypothesis tests and construct the confidence intervals. We could, if we were very eager, calculate this variance by hand. It is possible because we know the value of xi, we know mu x, or we could approximate mu x using x bar. We know ui, the OLS residual. We know n. We know the variance of x. Okay, so we could calculate this by hand if we were very eager. However, we have Stata to help us carry this out. Alright, so this construct is going to help us carry forward the hypothesis testing confidence intervals.